Hello everyone. In this video, we're going to be discussing a very important topic that came up recently. So the reason why I titled this video with why 2 to the power x does not equal 0 is because Black Pen Red Pen, as you know, made a video a few days ago. It's probably more than 4 days ago when I took the screenshot. But in that video, basically the title says I thought 0 to the power x equals 2 was impossible. Well, that's what we're going to explore. I'm going to explain what dual numbers are and then try to answer some of the questions that are posed in that video and as well as clear some of the misconceptions, hopefully. Let me know what you think. Great, so this is what the beginning of the video looks like. 0 to the power x equals 2 is the original problem, so that's what we're trying to solve here. And then the definition of a dual number is basically we have a number called epsilon, and epsilon squared is equal to 0, but epsilon does not equal 0. It's kind of like the I, where I squared is -1, but I does not equal -1. And we can write complex numbers, and if you're into complex numbers, go ahead and check out my other channel, aplusbi. So I'm hiding that part because that contains the steps to the solution, but later on I'm going to show you what the solution steps look like. Okay, so let's go ahead and start by defining what dual numbers are. Now, dual numbers are actually pretty interesting. Somebody thought of this idea. Basically, the definition is we have a number epsilon, which is not 0, but its square equals 0. So it's a very, very small number. By the way, it just models an infinitely small number. And guess what? Dual numbers can be used for automatic differentiation. It's something that is actually used by computer science people. Anyways, let's go ahead and define the dual number now. So a dual number can be defined as a plus b epsilon, where a and b are real numbers, just like a complex number a plus bi. But in this case, we replace I with epsilon. A and b are real numbers, and a is called the real part, and b is called the dual part, as far as I know. So this is a dual number, okay? And we're going to be using some Taylor series, a couple different things, to prove some important identities, because these identities are critical to understanding what dual numbers are and what they're used for. Okay, so let's go ahead and start with Taylor series. So as you know, or you should know, we can write f of a plus h. You can also write it for f of x plus h, but I want to use a particular value, which you'll see why in a little bit. This is equal to f of a, and this is easy to prove, by the way, plus f prime of a multiplied by h. And then what we do is basically we keep differentiating at a, and then whatever the degree, the level, however many times we differentiate, we divide by that number factorial, and then multiply by h to the power that number. So hopefully you get the pattern, and the next one is going to be f triple prime a, divided by 3 factorial times h cubed, and so on and so forth. That goes on forever. Obviously, this is an infinite polynomial because we can do this for any function that is differentiable at a. Infinite many times, of course. Now, in this equation, if you replace h with b epsilon, you get something amazing. You get f of a plus b epsilon, which is basically the image of a dual number under f. And if you just replace a with h with b epsilon everywhere, f of a is not going to change, obviously. Then you're going to get f prime of a multiplied by h, which is b epsilon. And then the next term is going to be f double prime of a divided by 2 factorial. This is the critical part, b epsilon to the second power, so on and so forth. You don't really need quite a few terms to understand what this goes, what's happening here, because this is where the criticality starts. So now f of a plus b epsilon is equal to f of a plus f prime of a, nothing interesting so far, right, times b epsilon. I've noticed that when you expand b epsilon to the second power, you're going to get b squared epsilon squared. But guess what? We know that epsilon squared is equal to 0. This is the most critical part, so that this term becomes 0, and everything that follows becomes 0. So we get a finite sum here, which is amazing, don't you think? And of course, we can write it in a slightly different form to reflect the fact that we're dealing with dual numbers. So f of a plus, the next part is just going to be b f prime of a epsilon. So again, this is a dual number because if you think about it, this is kind of like x and this is kind of like y, and we're looking at something like x plus y epsilon, which is in the same form as a plus b epsilon. Does that make sense? So this is the first identity we're going to be looking at. So I want you to go ahead and pay attention to what's happening here. This is actually beautiful. And what it gives you is, if you evaluate f at a plus b epsilon, then you basically get the function value and its derivative. That's why this is used for automatic differentiation. Let's go ahead and take a look at a particular example, shall we? Now suppose f of x is equal to ln x. Now tell me what f prime is, right? The derivative of ln x, hopefully everybody knows it. It's 1 over x, right? Now, if you evaluate f of a plus b epsilon for this particular function, you're going to get ln of a plus b epsilon, right? And then by definition, by this, the identity that we just came up with, f of a is just going to be ln a. Of course, this requires that a is greater than 0 because we want it to be a real valued ln, right? Not like a complex logarithm. Plus b times f prime of a. This is f prime. If you evaluate it at a, it's going to be 1 over a. And then it's going to be multiplied by epsilon. Guess what that's going to turn into? Ln a plus b epsilon can be written as ln a plus b over a epsilon. So a couple things you need to be careful about here. One, a needs to be greater than 0. I already talked about it. Second thing is you don't want a to be 0. Obviously, if a is positive, it can't be 0, can it? No. So we're good on that one. As long as the real part of our dual number is positive, we are able to evaluate the ln of that dual number. So log is only defined when a is positive. Does that make sense? In other words, if a is equal to 0 and b is equal to 1, what happens? You get ln of epsilon equals ln of 0 plus b, which is 1, over 0 epsilon. Uh-oh, Houston, we have a lot of problems, not just one, right? ln 0 is not defined, 1 over 0 is not defined, so we run into a problem. You know what that means? That means ln epsilon does not exist. Now, why did I say that and why do I keep saying it? Because this is going to come up later as I will show you in the solution of this problem in Black Pan, Red Pan's video. Okay, so a couple other things that we can talk about regarding epsilon. Epsilon is nilpotent and it's not invertible. What that means is nilpotent basically means if you take an element and then raise it to some positive integer power and you get 0, that element is called nilpotent. In this case, if you raise epsilon to the second power, you get 0. Obviously, 0 is always nilpotent, but we're basically talking about non-trivial nilpotent elements. And why is that important? Because if you have a field, for example, like Z5, which is the mod 5, every non-zero number is going to be invertible. Okay? Anyways, that's a different story. I'm not going to get into the nitty-gritty. Maybe later on we can do some abstract algebra videos, and I can even turn it into a playlist probably. Even this one could easily be turned into a playlist because I think we're going to do more videos on dual numbers because it's an interesting topic. Now, another thing that I wanted to talk about, and I said that epsilon is not invertible. So let me go ahead and explain that real quick. If you suppose epsilon is invertible, then what that means is epsilon times another element, let's just call that y, should give you 1, the identity element of multiplication, right? Which means epsilon will have an inverse. And this y needs to be a dual number, obviously, because we're in the world of dual numbers. So let's suppose that we have a dual number in the form of a plus b epsilon. We multiply it by epsilon, and we get 1 from it. But wait a minute. How do you multiply epsilon by this? Use the distributive property. You get a epsilon plus b epsilon squared. Uh-oh. We know that epsilon squared is equal to 0, so this will cancel out. We're going to end up with a epsilon equals 1. What is that supposed to mean? It means you're multiplying a real number by epsilon, and you're getting 1. But 1 can be written as b. So let me go ahead and write the 1 as b plus a epsilon. Actually, 0 plus a epsilon, that's what I meant, right? But wait a minute, the real part of this number is 0. But the real part of 1 is 1 because 1 is a real number. Therefore, this is not going to work. In other words, epsilon does not have an inverse. So 1 over epsilon is basically not well defined. Okay? So the third thing that I want to talk about is when you write the natural log, right? Remember we said that ln of a plus b epsilon can be written as ln a plus b over a epsilon. I think in that video, another thing was mentioned, like with the case of complex logarithms, you know how with complex logarithms of a complex number, we have the ln of the absolute value, and then we have the I times the theta, but we also add something like 2 pi ni, right? So this additional piece does not show up with dual numbers. Why? Because if you look at the dual number exponential, it has kernel 0. What does that mean? Maybe we can talk about that later. But anyways, let's go ahead and see what all this means. First of all, let me remind you one more time that ln epsilon does not exist. Okay? So let's go ahead and go back to the part of the video where we have the solution. Let me go ahead and open this up. And here we go. Ta-da! Now you can see here that if you natural log both sides, of course you have to write 0 as epsilon squared, which is what it is. But then when you do the log and use the properties, you're going to end up with something like ln epsilon, which does not exist. Does that make sense? Therefore, the solution is not valid, and there are no solutions to this equation. Okay, so since we clarified it, let's go ahead and talk about another thing. Like I told you that dual numbers are used for automatic differentiation. So let me go ahead and show you another example that will hopefully make this more clear. Suppose f of x equals x squared. Now let's go ahead and evaluate f of x plus epsilon, which is a simpler version of what we did before. But this is a lot easier to understand. What is f of x plus epsilon? Since f of x is x squared, it's just going to be x plus epsilon squared. If you expand this, you're going to get x squared plus 2x epsilon plus epsilon squared. You know the identity, right? But epsilon squared is equal to 0. This is just going to give us x squared plus 2x epsilon. And what is that supposed to mean? Let me go ahead and show you. If you write it again, this basically means that we have a function, f of x equals x squared. You do see the function here and its derivative here. That's how we can basically get the function and its derivative without going into the limits as h approaches 0, blah, blah, blah. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and make sure to check out my other channel, aplusbi, where I talk about complex numbers in great detail. Until next time, bye-bye.